this video, we're going to talk about phase changes and phase diagrams. So phase change is when a material converts from either solid to a liquid or liquid to a gas or gas to a liquid. And we'll talk about the conditions required for several materials to make those changes occur. But first, I want to just point out, in general, what's happening at the molecular level when you have a transition between phases. Here we have oxygen, which is a nonpolar diatomic molecule, or element, and right now it's in the solid phase. You can see that the matter is packed very close together. The molecules have the permanent neighbors, they're not moving around and finding new partners, and you can see that the density is relatively high. There's not a lot of interstitial space here. As I heat it up, what's going to happen is it's going to eventually increase the kinetic energy to the point where the oxygen molecules can slide past each other and make new neighbors. And now we would be in the liquid phase. Now, even in the liquid phase, you're going to have some molecules that have enough energy to evaporate. But when you're looking at oxygen as a liquid, in general, it's similar to solid in the fact that it's still pretty dense, but there's a little bit more interstitial space in there between the molecules, and therefore, it's a little bit less dense than the solid phase. And this is what happens for most materials, and we'll talk about water being different in a couple of minutes. Now, you can see that there is not too much of a difference between the solid and the liquid phase. However, there is a substantial difference between the liquid and the gas phase. And what's happening when a material goes from a liquid to a gas is it's completely overcoming the intermolecular forces that exist between the molecules. Going from a solid to a liquid, you're just basically inputting enough energy so that they can slide past each other, as opposed to completely break apart, which requires more energy. And how strongly these molecules stick together will determine the conditions under which they boil, which conditions under which they melt. So basically how strongly they're stuck together and how the pressure and temperature need to be influenced to account for that. So we said that in general, as you add kinetic energy to it and increase the temperature of the material, it's going to become more likely to boil in the liquid phase. So another way we can manipulate the boiling point of a material is to adjust the pressure. So we're going to look at water right here, and I'm going to put this vacuum pump on. When I apply this vacuum pump, what's occurring is the air is being pumped out of this container and reducing the atmospheric pressure on top of it. And what you're going to see, and this is all room temperature, I'm putting my hand on this because it is room temperature, but what you're going to see is after a minute that the water is actually going to start to boil at room temperature. So without manipulating the pressure and adding any kinetic energy, the water will be able to boil under the altered pressure conditions. And in a minute, we're going to go back and we're going to look at a phase diagram and talk about how we can actually look at what temperatures and pressures are required for these transitions to occur. So we also saw that in the phase diagram, as you increase the pressure, it's going to favor the liquid phase. That's because it shifted back like this. You increase the pressure, you're going to go from a solid to a liquid. So here I have ice in the solid phase. You can see the water molecules aren't making new neighbors. As I increase the pressure on this substance, you end up converting. Now the solid became a liquid. So increased pressure resulted in it favoring the liquid phase. So here we're going to look at the phase diagram for water, and we're going to look at what the phase diagram shows us. It is a comparison of what phase you're going to be in at given pressure and temperature conditions. So you have the solid, liquid, and gas phases, and these lines represent the changeovers, so the phase changes. When you're going from a solid to a liquid, that's when you're melting a substance. When you go from a liquid to a solid, that's when you're freezing a substance. When you go from a liquid to a gas, well, then you're boiling. And then if you go from a gas to a liquid, you're condensing the vapor into a liquid form. Now, when you have a system that is in a set of conditions where it's exactly on the line, for example, if you're at the freezing point of water, since this is water's phase diagram, water has at a pressure of 1 atmosphere, freezes at exactly 0 Celsius. That's what the scale is based off of. Now, if you have water at 1 atmosphere and 0 Celsius, you're going to have the system in equilibrium, assuming no more temperatures not increased or decreased at this point. So what I mean when I say that they're in equilibrium, the solid is melting into a liquid at the same rate that the liquid water is then freezing back into a solid. So the reverse processes are happening at the same rate, so you end up with no net change in the amount of materials. If you increase the temperature at that point or start adding kinetic energy to the system, well, then you're going to undergo the phase change that would favor the production of the liquid. If I started cooling it, then you're going to have a phase change that favors the production of a solid. So that's what I mean when I say this is an equilibrium state, when you're going from either one, if you are at conditions that are exactly on the line. Now, at 1 atmosphere of pressure, you also have water boils at 100 degrees Celsius. And what that means, again, is that at that point, if you're at those conditions and you're not adding any heat or you're not removing any heat, you're going to be at equilibrium between liquid and gas phases. So that means gas is going to be converting into the liquid at the same rate that the liquid is converting into a gas. Now, if you add more energy to the gas, well, then you're going to be shifting to the mixture, then you're going to be shifting it to the gas phase. If you cool it down at that point, you're going to be converting it to a liquid. Now, you can heat up water only to a certain point. Once you heat it up to a certain point, you reach a critical point. And that is the point at which the liquid and the vapor phase become indistinguishable. All right, so basically, past the critical temperature, you're not going to have any liquid. And if you have the critical pressure is the point, like the minimum amount of pressure required at that critical temperature to make it condense into a liquid. If you go beyond those two parameters, you end up with a supercritical fluid where you can't really distinguish the phases. So that's how we interpret this phase diagram. One other thing I want to point out with respect to water is that it's unique in that it goes, this line right here between the solid and the liquid phase goes backwards. Most materials, it actually slants forwards. The reason that water goes backwards is because water, uniquely, is less dense as a solid than a liquid. We know that because ice floats, right? So if you have conditions where the pressure is increased, it's going to favor the higher density phase. So if you go up in pressure from normal atmospheric pressure, if you increase the pressure, it's going to, at the freezing point that it would normally be, it's going to favor the liquid phase because it's going to want to be in a less, if you have a lot of pressure pushing down on it, it's going to want to condense the material as much as possible. If you reduce the pressure at that point, well, then you can end up in the solid phase still at 0 degrees. So you can manipulate the pressure to influence what phase it's in at a given temperature. We've also seen systems where we, again, boil water at room temperature. We can do that by lowering the pressure, and then when the pressure is reduced, you can see that it then will convert from the liquid to the gas phase at a temperature less than 100 degrees. Now, one other thing that you don't usually see for water, but you can see for other materials like carbon dioxide we'll look at in a minute, is sublimation. That's when you go directly from a solid to a gas, or you could have the reverse process, which is called deposition. The reason we don't usually see water go straight from a solid to a gas because the pressure required for that to occur is down to 0.006 atmospheres. So less than 1% of our normal atmospheric pressure would be how low you'd have to drop the pressure to in order to go from a solid directly to a gas. So we don't usually see that. And this point right here, the triple point, is the point at which the temperature and pressure conditions in which all three phases of water would be in equilibrium at the same time. So you would have solid, liquid, and gas present in the sample all interchangeably and in equilibrium with each other where it's going back and forth between all of the phases. All right, so now we're going to take a look at carbon dioxide and see how that's a little bit different. So carbon dioxide is, again, like I said, the line here shifts going from solid to a liquid goes forward because solid CO2 is actually more dense than liquid CO2. But we don't usually see liquid carbon dioxide. It usually sublimes. It's called dry ice for a reason. It never becomes a liquid at normal pressure conditions. The reason for that is the triple point we observe, where again you can have sublimation when you're to this side of the triple point, is at 5.19 atmospheres. So you would need over 5 times the atmospheric pressure in order to get it to go from solid to a liquid before converting to a gas. So very high pressure required. And if you think about this, water requires such a low pressure for this. Carbon dioxide requires a high pressure. So to get water to become a liquid, because its intermolecular forces are so strong and hold it together so much, you don't have to compress it to make it into the liquid phase. Whereas carbon dioxide is very nonpolar. It'll just fly apart when given enough kinetic energy. There's not much holding it in place. So therefore you really have to cram it all together to let its only London dispersion forces hold it in place. Okay. One more thing I just want to talk about is vapor pressure for different molecules as a function of temperature. So earlier in this year we did a lab where we had to collect hydrogen gas over water, and we had to account for the water vapor pressure, and we learned that that was a function of temperature. But why? When you increase the temperature of a material, you increase the average kinetic energy. And for a substance to escape the liquid phase, it has to get enough energy to basically break away from its neighboring molecules and overcome the atmospheric pressure pushing on it. So here are three molecules that increase in polarity as you go from left to right. Water being the most polar, it has hydrogen bonding, it's like super duper dipole. And then this one barely being polar. All right, so you can see that at any given temperature, let's say 40 degrees for example, water has the least vapor pressure. That means it's exerting the least force at the surface of the liquid, and essentially means it's the least likely to vaporize at those conditions. If you look at this diethyl ether, which is less polar, it will effectively be boiling at that point. So ethanol is kind of in between. So as you increase the strength of the intermolecular forces, it's going to decrease the vapor pressure exerted by that material because it's going to be less likely to break away from its solution and contribute to the pressure as a vapor.